Assalamu alaikum everyone. My name is Shah Abdullah and I am an engineering student currently studying at Air University Islamabad, and hope you are all doing fine. And today I'm gonna discuss the topic another digital logic design lab, lab number 3, and the main objective or the topic of this lab is about implementing Boolean arithmetic, implementation of Boolean arithmetic using logic gate ICs and verifying De Morgan's law. Now we shall see that what is a De Morgan's law. De Morgan's law equation looks like this. That first if we see that x plus y, uh, we call this as a knot. X or y in the if we talk about De Morgan's law in case of or in the words of digital logic design, so we can say that these are two inputs x and y, and we can say that this equation is being stated as x or y whole or complement, or this complement is known as knot. So x or y whole knot, which is equals to x naught and y naught. So we can see here. So let's see this, how we can implement this on our software named Proteus. First of all, we shall see. Oh yes, this is the one. Now we shall see that this is the left hand side of the equation, which was x plus or x or y whole complement or not. So here we can see that these are two our inputs generated by logic toggles, which give 1 and 0 the Boolean expressions, and this is an OR gate whose library in the Proteus is 7432. The IC name of OR gate is 7432. This is a NOT gate. The IC name of NOT gate is 7404. And if we see in this left hand side of the equation of the De Morgan's law, x plus y, x or y whole knot. So first we shall see that here it is x and here it is y, and then these two inputs are added by an OR gate, and then the whole OR gate is then reversed, or you can say inverted. We cannot say reversed, we can say it is inverted. And let's see from the truth table that what shall happen if we give two of our inputs 0, x and y, 0 and 0, 0 and 0. Let's start the simulation. So here we can see it is giving us 1. Now we shall see that what our logic truth table is saying to us. 0 and 0 gave us 1, so hence this condition is true. Now we shall see another condition. We can say make y as 1. So when we made y as 1, our output gave us 0. The logic probe gave us the output 0. Now if we give both of our inputs 1, the result is same. Now we shall see that in our truth table, 1 and 1 gave us output 0. So now this was all of our left hand side of the equation. The equation was basically this first equation, and we simulated this part only, the left hand side. Now we shall see the right hand side. This is the right hand side. these are two of our inputs supported by or generated by input toggles. So logic toggles, we can say that. And these are two NOT gates to invert these two inputs as x naught and y naught, and then multiplying them or giving a product by attaching these two inputs to an AND gate. The IC number of AND gate is 7408. So let's see. We shall see the truth table first. This is our truth table, x prime and y. If we see that x and y are 0 and 0, this means our x prime and y prime will be 1 and 1. And let's see what x prime and y x naught dot y naught product gives us. We shall look at this table first. Sorry about that. This is the main table of the first equation. So we shall see here, if we give both of our inputs 0, our inverted outputs will be 1 and 1, and furtherly, if we join them through an AND gate, our output should be given as 1. So let's see, ignore this, now concentrate on this circuit. As we said earlier, if we gave both of our inputs 0 and 0, it will be inverted as 1 and 1, and as we know in that truth table of AND gate, 1 and 1 gives us an output of 1. Now let's see if we give 1 to our y. Now we shall see in the truth table what our truth table gives us an answer or output. We gave y a 1, so 0 1, which is inverted as 1 0, and furtherly our output, when we join these two outputs to an AND gate as an input, so the output given by 0 and 1 is 0. Now let's see if we on both of our inputs, the result is same as we can see in the logic truth table, 1 and 1, which is inverted as 0 0, and when they are joined by an AND gate, our output is 0. So that was the condition for, hence the De Morgan's law is verified. We can see here we implemented De Morgan's law using logic gate ICs, and now we shall see this second equation. So this is basically our second equation, and this is the left hand side of the equation, and this is the right hand side of the equation of the De Morgan's law. And here we can see that in first in left hand side, at left hand side we can see that basically there are two inputs which are joined by an AND gate, and then further they are joined by a NOT gate. And in the right hand side there are two inputs, and these both are joined by these both are inverted and then joined at a NOT and an OR gate. So let's begin the simulation. First we shall off these, and we shall look at the truth table, that when we gave 0 and 0 here at the inputs, so 0 and 0, so we shall see that, as we know, 0 and 0, 0 and 0 gives us an input of 0, and 0 when it is inverted by a NOT gate gives us an output of 1. Now let's see another condition, 0 and 1, make y as 1. So here we can see the result is still same, as 0 and 1 gives us an output of 0, x dot y. 0 and 1 gives us 0, which is inverted by a NOT gate, and our output gives us 1. Now we shall see when both of our inputs are 1, the result is 0, as we can see in the truth table as well. 1 1, and it is inverted. When it is 1 and 1 gives us an output at the AND gate as 1, which is inverted by a NOT gate, and hence our output gives us the answer of 0. So this is for our left hand side. Now we shall see that in our right hand side. This is the right hand side of the De Morgan's law equation. This one, x naught plus y naught. Now if you see here, there are two inputs x and y. These are two of our inverted outputs as x prime and y prime, and further we connected these inverted outputs as the input of OR gate, which gave us the logic of x naught plus y naught, and this is our answer. So let's begin the simulation. We shall first look at the truth table. Here it is our truth table. If we gave 0 and 0 at the logic toggles as our inputs, so 0 and 0 are inverted as 1 and 1, and when they are furtherly joined on an OR gate, so we can see 1 or 1 gives us an output of 1. Now we shall see when now let's begin as 1, which is given to x. The result is still same. 1 it is inverted as 0, 0 it is inverted as 1, and 0 or 1 gives us, as we know, the truth table of OR gate, it gives us the output of 1. Now when we see that both of our inputs are 1, the result will be 0. Now let's see how. As 1 is inverted by a NOT gate as 0, and same case with y, it is inverted by the NOT gate as 0, and 0 or 0 gives us an output of 0. So hence our logic gates are proved. So here we can see when both of our inputs here and both of our inputs here are 1 1, so our outputs are 0. So that's how we verified De Morgan's law, and there this is just an implementation of a Boolean expression or Boolean arithmetic equation, we can say. Now let's see if we follow the truth table. Here is the equation, and here is its truth table. So if we give 1 to x, x is directly attached to the terminal of OR gate, and y and z first are connected to an AND gate, and furtherly its outputs are connected to OR gate. So here it is our output x or y dot z, y and z. So if we see that 0 and 0 are given at y and z, so 0 0 0 and 0 gives us an output of 0, and x is since directly attached to our OR gate, so here we can see 1 or 0, y dot z, y and z gave us an output of 0, so here we gave 1, so 1 or 0, as we obviously know that in the logic truth table of OR gate, 1 or 0 gives us an output of 1. Let's see here, 1 and both of 0 gave us 1. Now we should try another when all of them are 1. The result is still same, as we know that if we solve first this AND gate, that is y and z, since both of the inputs are 1, so our output will be 1, because when both of our inputs are on or actively high in AND gate, in case of AND gates, so it gives, the AND gate gives us an output of 1, so 1 or 1 gives us an output of 1. And that's all for today's lab. Hope you liked it and got the necessary information you needed. And that's all.